everyone. I am Dr. R. Soumya, Assistant Professor, Department of Electronics and Communication Engineering. Today we are going to see the subject sensors and actuators. Unit 4 is automotive actuators. Here we are going to see the topic three-phase machines. The three-phase linear electric actuators works to convert the energy into the linear motion. They are typically used in industrial applications where high loads are required. The three-phase electrical motor uses a three-phase power supply to convert the electrical energy into the mechanical energy. It contains 4 wires and uses 3 alternating current of the same frequency. Since it generates a rotating magnetic field, it does not need a capacitor for startup. Types of three-phase electric motor. These machines convert the electrical energy into the mechanical energy. Induction motor, squirrel cage induction motor, simple and robust design. It is commonly used in the industrial applications. Next one is the wound rotor induction motor. It is equipped with the slip rings and external resistance for the speed control. Next one is the synchronous motor. It operates at the constant speed. It requires the external DC source for the rotor excitation. Next one is the permanent magnet synchronous motor. Rotor uses the permanent magnetic instead of windings. High efficiency, often used in the robotics and electrical vehicle. Brushless DC motor operate an three-phase AC but minimum DC motor characteristics, used in applications requiring high reliability and efficiency like drones and applications. The three-phase induction motor. The motor is used to convert the electrical form of energy into the mechanical form. According to the type of the supply, motors are classified as AC motors and DC motors. In today post, we will discuss the different types of three-phase induction motors with working principle and applications. The induction motor, especially three-phase induction motor, are widely used AC motor to produce mechanical power in industrial applications. Almost 80% of the motor is a three-phase induction motor among all motors used in industries. Therefore, the induction motor is the most important motor among all other types of motors. Stator, the stationary part of the motor, housing the windings where the three-phase AC supply is connected. It generates the rotating magnetic field when powered. Next one is the rotor, the rotating part of the motor located inside the stator. Induced the current in the rotor creates the torque, causing it to rotate. Shaft, connected to the rotor, it transmits the mechanical output to the load. Three-phase AC supply, it provides the electrical power to the stator winding to generate the magnetic field. Next one is the magnetic poles, represents the north and south poles of the rotating magnetic field created by the stator. Next one is the working principle. Stator winding and three-phase power supply. The stator has a 3 set of windings placed 120 degree apart electrically. When a three-phase AC supply is connected to this winding, it creates a rotating magnetic field. This field rotates at the constant speed called synchronous speed. Next one is the rotating magnetic field. The three-phase supply causes the current in each stator winding to vary the sinusoidally. This creates the magnetic field that rotates around the stator core. Next is the rotor construction. The rotor can be of two types, squirrel cage rotor and the round rotor. Next one is the induction of the EMF in the rotor. As the EMF is cut through the rotor conductor, it induces an electromotive force EMF in them according to Faraday's law of the electromagnetic induction. This induced EMF causes a current to flow in the rotor conductor since they are shorted in the case of squirrel cage rotor are connected to an external resistance in the case of wounded rotor. Torque production. The current flowing in the rotor conductors create its own magnetic field. The interaction between the rotor's magnetic field and the stator's RMF produces a torque in the rotor. Rotor speed and slip. The rotor speed is represented as N, or will always be slightly less than the synchronous speed Ns. The difference between these speeds is called slip. Back EMF and rotor current. As the rotor starts rotating, it cuts the stator's magnetic field at the reduced relative speed. This induces a back EMF in the rotor winding, which opposes the original induced EMF. The net EMF across the rotor winding decreases, reducing the rotor current and the torque. Working principle. The DC supply creates a magnetic field on the rotor. The stator three-phase winding generates a rotating magnetic field when powered. The rotor locks the rotating magnetic field due to the magnetic attraction, and the magnetic runs at synchronous speed. If the frequency of the AC supply is F Hz and the stator is wound for P number of poles, then the speed of the rotating magnetic field is given by Ns equal to 120 F by P. The stator is wound for the similar number of poles as that of the rotor and feed with the three-phase AC supply. The three-phase AC supply produces the rotating magnetic field in the stator. Now the stator poles are revolving with synchronous speed. If the stator position is such that N pole of the rotor is near the N pole of the stator, then the poles of the stator and rotor will repel each other and the torque produced will be anti-clockwise. The stator poles are rotating with synchronous speed and they rotate around very fast and interchange their position. But at this very soon the rotor cannot rotate with the same angle, and the next position will be likely the second schematic in the figure.